Today I'm going to talk to you guys about our submission to the Recommender Systems 2020, our demo entitled AutoRec and Automated Recommender System. So this is the work between me, myself, Sean, and other five members of the Texas A&M University from the data analytics at the Texas A&M laboratory. Okay. So our demo is trying to first we identify some of the common challenges faced by the recommender systems. Well, the first one is that so in the modern days, the models of recommender systems often become obsolete relatively quickly due to the specificity of these models. One of the reasons is that the data evolves with time. In modern days, a lot of data being collected every day, so it's likely a lot of new types of data are going to be added to data sets. For example, the dense data set might start to be collecting the sparse data. So now a model not only have to handle dense data but also sparse data, and also the new tasks might be added. For example, like in my experience in the music recommendation companies, in the beginning they might be recommending individual songs by analyzing their rating information, but then they move on to suggesting a playlist to users, and that becomes a CTR problem. And also, when you are trying to explore new models, you are facing huge search space because of the substantial amount of potentially suitable models in out of the blue. That and also it requires a very scenario specific expertise to tune the hyperparameters for a specific model. So basically, you have to be familiar with not only the model, but specifically how to use the model in a specific situation. And that requires a lot of experience. And that can make it hard for newbies or when they encounter a new problem, a new recommendation problem. So there are three focuses of the auto recommendation demo. The first one is adaptable, and then automated and then user friendly. By adaptable, we want the framework to contain modules that can handle different recommendation scenarios. As for automated, we want to be able to automatically identify suitable model and tune the hyperparameters for, and they also have to get good performance in order to be valuable. And also, it has to be user friendly, so it has to be intuitive to use with a few lines of coding, so simple coding, and we want the API to be very familiar, so the public have to be already familiar to it. So in order to enforce adaptability, we have implemented adaptable block design. So for our block design, there are three major modules. As you can see, for the recommender parts, there is the mapper and the interactor and the optimizer. As you can see from our code, the pipeline is composed of the interactor, the mapper, and the optimizer. So for the mapper is mainly responsible for enforcing data adaptability. Namely, it can handle both dense and sparse data. For example, the DeepFM model needs to be trained on, when it's being trained on the critical data set, it has to handle both the dense and the sparse data. As you can see here, when we build the DeepFM model, it requires both the sparse and the dense data. When we move on to the interactor, the interactor is responsible for enforcing model adaptability. Namely, it can support many deep models as well as our AutoRec models, which I'll talk about it later. And as of currently, we have made sure that our model can find all these models: DeepFM, DRM, CrossNets, AutoInt, MF, MLP, and the NeuroMF. And as for optimizer, it is responsible for enforcing task adaptability. So it allows our model to do both the rating prediction task and the CTR prediction task. And next, we move on to how to make a recommender system model automated to automatically search the model and hyperparameters, and also with good performance. So in order to do an automated search on a recommender system model, system model, we need to have a recommender object, as you can see here, and a searcher object. The recommender object is responsible for assembling the main model and also provide a search space in each of the modules, a search space for the mapper, the interactor, and optimizer. And then combined with the searcher, it contains the tuner to search the best model as well as the hyperparameters from each of the modules. So here, the recommender, the model search space, this is the hyper interaction is our novel implementation. It can stack many layers of the interactors from different models together. As you can see here, in the interactor, the hyper interaction contains different types of interactors, and all these interactors also contains hyperparameters. So for the model search, we'll search using the hyper interaction, and you can also stack different numbers of layers of the interactors. As for the hyperparameter search, you have already seen for different interactions, they have their own interactor specifications. For example, for the MLP interaction, it has the units, layers, and dropout for hyperparameter search. As for the searcher, currently it contains 3 kinds of tuners: random tuner, greedy tuner, and Bayesian tuner. So we have already shown that our model can search both the model and hyperparameters. However, it won't be valuable if it does not have good performance. So here in this section, we are going to show you the performance of our model. So for the rating prediction task, we are testing on the Evazoo and Critical dataset with 500K amounts of data. From this table, you can see all these numbers are actually the log loss, so the smaller the better. And here, using our automated search on hyperparameters, the cross-site model being optimized can find the best results with the lowest loss. However, using the AutoRec, which is our model trained using the hyperinteraction interactor, it can search both the model parts and the hyperparameter parts. And as you can see, without any prior knowledge, our model can search the best model and find a second place model. And not only our searcher works very well, our recommender also works very well because all the numbers are generally on par with this amount of data. And therefore, with the robust recommender and the robust searcher, we have a robust architecture. And also, let's move on to the CTR prediction. For the CTR prediction, it's tested on the movie lens YM full dataset and the Netflix full dataset. And the numbers reported here are the MSE losses. As we can see, the AutoRec model not only finds the best model, but also finding the second place best model. So here also we have the robust recommender because all these numbers are on par with the benchmark numbers. And also we have robust searcher because now it can not only search the best model, but also the second best model without any prior knowledge. And that give us a robust architecture. And the third goal of our demo is to show how we provide an easy-to-use API. So for our API, first of all, we built our AutoRec based on the TensorFlow ecosystem. And with the TensorFlow ecosystem, we can benefit from the regular updates from the Google. And also, it allows us to export model as the Keras model instance very easily. So the users, after they find the best model and the best hyperparameters, they can simply export the model for next use. As you can see here, the ecosystem, the TensorFlow is the most basic fundamental basis. And then we have the Keras ecosystem. And our AutoRec is built upon it. And next, we are showing that our code requires only minimum coding. In about 10 lines, you can get a trainable and searchable model. Here is the actual code of our RecSys, of our AutoRec model. Here requires only 10 lines to build a model that is both trainable and searchable. And third, our platform has an intuitive API. Here, as you can see, the way we use it is to declare a mapper and then feed it to the declared interactor. And the interactor is being fed into the declared optimizer, and the optimizer is being fed into the declared searcher. So this is a typical computational graph. It requires only declaration, chain, declaration, chain, declaration, chain, declaration, and then just do the actual search function. So for conclusion, the merits of our platform is that it's adaptable. It's adaptable in terms of the data, model, and task. The data, it can handle both sparse and dense data. In the model, it can support more than 7 kinds of models, and task, it can handle both the CTR prediction and rating prediction. As for automated, our platform can support both the model search and the hyperparameter tuning with robust performance. And this is easy to use because it is built on the TensorFlow ecosystem, requires only minimum amount of coding, and it has intuitive API enforced by the computational graph. For our novelty, to our best of our knowledge, we are the first to leverage AutoML for model search in deep recommendation models. And here, we show the demo resources we have already uploaded to the GitHub. Here's the GitHub repo address, and also we provided benchmark that we tested. And now I'll be showing you guys that our code is runnable. So as you can see here I'm going to run the DeepFM model on the CTR task using AvaZoo dataset. Again, you can see with a few lines of code, you can build a model that is searchable and trainable. Now I'm going to train the model. So now the model is loading and preprocessing the dataset, showing how much splits of the train and test data, and it starts training. When it starts training, it's going to search for the best hyperparameter, because in this case, the DeepFM model has already predefined model, but its hyperparameters are searchable. So here, we start to search on the different kinds of hyperparameters. And for the benchmark, if you click on the link, as you can see, it's functional. We have reported our tested benchmark and in dataset information online in the GitHub repo. So for the future directions, for the inputs, we want to support multimodal data such as the image, video, and sound, and that will allow us to explore to more kinds of recommender models. And for a search space, we want to enrich the block candidates, for example, adding new model interactions. And we also want to add more examples to provide more plug-and-play examples for the users. So for our background, we are coming from the data lab. Data lab is led by Dr. Bang Hu, and also it is from Texas A&M University. And our lab is also the creator of the AutoRec toolkit. It is integrated into the official TensorFlow ecosystem, and it receives 7.1K stars on GitHub. And it does the efficient neural architecture search. As for our team expertise, we have the original AutoRec crew in the team developing the AutoRec platform. Also, we have publications on both recommender systems and automated machine learning conferences. Thank you very much.